All right, let's get started. So first of all, thanks everyone for coming. And in the next 40 minutes, I think me and Sergey want to share a story of DoorDash, of how DoorDash make the decision of this Iceberg table format adoption, and also our decisions of a unified metadata catalog implementation in the Lakehouse platform. And first, quick around the board for the intro, and you want to do first, Sergey?
Sure. Hi. Hi, everyone. My name is Sergey Zavgorodni. I lead data engineer at DoorDash for over 3 years now, mostly focusing on what we call internally core or foundational projects, including development of various frameworks, including the data lake-oriented frameworks, recently focusing on the data lake, including Iceberg format adoption, and previously worked at different big and small companies, Disney Streaming, Yellow Pages, Cerner, and some small startups like DollarShave.com, if you heard it. So definitely very excited to represent today our journey in adoption of the Iceberg format and considering balancing different options that we went through. And want to introduce Ruotian, who has been a great contributor and one of the key decision makers to that whole project. So please.
Yes, thanks, Sergey. So my name is Ruotian. I've been in the industry for around 7+ years, and currently a software engineer at DoorDash. And then before and during DoorDash, I was in AWS/Amazon for around 5 years. So that's about me. Here's the agenda. We'll start with an introduction of DoorDash and DoorDash Data work, and then we want to jump into the DoorDash Data journey. Really want to describe what was happening in the past couple of years, how DoorDash Data work was formed and evolved, and what are the challenges we are facing. And then one principle we want to advocate and also want to emphasize is read once, read everywhere. And how we are going to choose Iceberg to achieve this table interoperability and how to make it work. And then the first part is practical explanation. I think Sergey will cover how are we going to do the implementation to achieve this goal. And then finally is lesson learned, and then we'll come to the end of the QA. Yeah, I think that's the agenda. First, hopefully everyone already heard about DoorDash and used DoorDash before. So DoorDash is a technical company mission to empower local economies by connecting people with the best in their city. Our vision is to connect every local business to every local consumer and bring them things in minutes, not days. And then we are at Foundation Data at DoorDash. So the vision for our work is to our product and the business decision should be data-driven. And this is our data scale. So we currently have around a couple of 100 petabyte data stored within Snowflake, Delta Lake, and Iceberg. And then our workload is we're currently serving around tens of millions queries and Spark job on a daily basis. So this is our DoorDash data scale and workload. Next, I'm going to jump into the DoorDash data journey. So I'm going to cut into a couple of different time spots. So let's first jump to the time before 2022. So at that time, DoorDash data org, all the business is still in the scattered world. So you can see in the upper part, so we primarily use Snowflake as a data warehouse, and then we build all the ETLs and load data from macro service DB, and then all the data we primarily use by the analytic team for all the business decision. And then on the bottom part, that's Databricks. So at that time, we only use Databricks Smart Compute. And for example, the use cases in the ML org, and then they build feature engineering frameworks and training inference all on top of Databricks, and then to serve all the existing ML use case. But the one thing to notice before 2022, I don't think we leverage any data catalog, especially for the ML use cases. All the data are either read in CSV or Parquet, and then we purely use Parquet read and writer to finish all the tasks. So that's what was in the 2022. And then time jump to the 2022 to 2024. We call that time of Delta Lake expansion. So on one hand, we continue our investment in the Snowflake side by introducing Snowpipe, which is our streaming use case. And also, we continue to build more complex batch ETLs, all flow into our data warehouse. And then we also leverage the secure data sharing, which Snowflake provided, and share the data to either accounting, PA, stand for people analytics, and also third-party vendors, etc. So you can see that's how we evolve in the Snowflake side. But on the other hand, we start the investment inside the Delta Lake, which means we want to fully adopt the data lake architecture. So we basically replicate the existing medallion architecture from Snowflake into data lake and leverage Glue as data catalog and start to build our data lake ecosystem. So the principle of data lake is we want to decouple all the individual components from the traditional data warehouse. So that's why you can see, so we introduced the CDC workload, we introduced the Flink workload, which is used for the real-time ingestion, and also we also have the CDP use case, which is a consumer data platform, the segment. So all the data will flow into our data lake. And then by introducing data lake, it also means we want to decouple all the components. For example, AWS Glue means for the data governance means we need lake formation, and the Unicatalog also provide RBAC. And since we have the Trino, which means we also need to implement Apache Ranger to achieve all the RBACs. And then for the BI reporting tools, so we have the Trino, which is used to do the cross-platform join between Snowflake and our data lake. And then the data hub is used to track all the data lineage and also track all the table tagging, all the things for the data discovery. Yeah, so you can see this is pretty much how we evolved inside this data lake ecosystem within DoorDash in this years. However, this sounds really nice, but it introduced some problem. So for example, if I'm a person in the data engineer org, and I want to access some data which ML team built, but ML team built, they all store inside data lake. And what we have to do is we need to build some egress, which is data copy operator to copy the data from our data lake into Snowflake to make the data accessible within Snowflake. Same thing for ML org. So for example, for the ML org, if I want to access some of the feature store, which is stored within Snowflake, and I still want to build some training job and to access the data. So in the past couple of years, what we have to do is we need to set up some JDBC connection. And the JDBC connection is nothing but we have to still use Snowflake compute to load the data from Snowflake into the Spark environment before we are able to leverage Spark compute to do the join and also finish all the data calculations. So the data copy and all those scattered, yeah. So the pain point is, so it introduced a lot of silos, and then the scattered data requires data movements for a lot of times. So, I mean, is there anything wrong for us to build a data lake? Absolutely not, because the good part is it is definitely cost effective for large-scale operation in data lake. For example, if we want to join all the terabyte or petabyte level data, so Spark compute is definitely much cost effective compared with Snowflake. And then also unlock wider range of data use case. So for example, ML use case, AI, all the use case, they all depends on all the Spark environment. So that's all the good part. But the pain point is, you can see this is a typical some workflow we built internally. So if we want to move the data across platform, it should go through this whole pipeline to make sure the data pass all the validation. And then when user want to just do some development from Snowflake into data lake, there are some syntax gaps. So it's really painful. And then, yeah, and also since it requires some data quality, freshness check, it is leading into a lot of operational pain. Then it jumped to our main principle or the goals. Can we achieve a goal that read once, read everywhere? But first thing is we need to consider our precondition. For DoorDash, both Snowflake and the Spark or Databricks are all remain business critical, and they all serve the different use case. And then in the past 3 years, we invested a lot inside our Delta Lake architecture, which means there are enormous existing Delta Lake table, which should continue to receive support. So that's the two main preconditions we want to accept here. And then the North Star goal is, so first of all, we want to eliminate data movements. Second is we want seamless integration of the query engine layer, including Snowflake, Databricks, EMR, Trino, and then we want a comparable query performance with existing Delta format table. And then we want improved development velocity across platforms like Snowflake, Databricks, EMR. And then Iceberg, so in the past a couple of years, we've seen all the ecosystem from the Iceberg involves a lot, which means if you look at the left side, both Trino, Snowflake, Spark, Flink, EMR, they can all rewrite from Iceberg, and then from the catalog level, Snowflake, Unicatalog, Glue, they all start to invest a lot into this Iceberg spec. So the Iceberg table can really achieve this interoperability requirements for us. So here are the decision so first of all, we want to still make sure we are the storage owner, meaning with all the data, it should be open table format. And we choose Iceberg table because it's open table format. It has snapshot isolation. It supports partition and schema evolution. It also has multi-engine interoperability, including Snowflake and Databricks. And then it also has the feature and the performance parity with Delta, and then it also cost-effective. And then the second thing is about the catalog. So when we think about the original data lake ecosystem within DoorDash, we need to maintain a lot of components. And if the data stay into multiple places inside our DoorDash, we need to just continue build one wrapper on top of another wrapper to make it compliance. So that's why we select Unicatalog, because Unicatalog is the state-of-art of metadata management, and it's open. It's a federated ecosystem, and then it supports multiple catalogs and table formats, and also it supports metadata caching and optimization. Of course, it has this centralized governance, fine-grained RBAC, PI, data discovery, and lineage. This really can simplify our internal process to provide our data user a better experience. And also another thing is, since we want to get data movements, metadata consistency is a key thing here, which means we need to make sure all the data resources should be identical within both platforms. For us, will be either Data Lake and Snowflake. And for Iceberg, so we can see it's guaranteed by internal Databricks and the Snowflake metadata integration. And for Databricks, we support GIT, foreign catalog integration, and also support HMS federation, which also a key thing for us because we previously used Glue. And this can provide us really a smooth transition process. And for Snowflake side, we have the auto refresh to make the metadata consistent. And we also observe there are some gaps. So that's why we also need to build some in-house data lake tooling to fill all those gaps to make sure this ecosystem is complete. Okay, so with all the decision making, I'm gonna pass to Sergey for the practical explanation section.
Hi. Thank you, Ruotian, for the great introduction and overview. Hi, everyone. I already introduced myself. My name is Sergey Zavgorodni. I'm lead data engineer at DoorDash, working on the architecture and technical design of the Iceberg table format adoption. So I'll walk you through technical details of what we internally call Project Fusion. When we started Project Fusion, our goal was simple but ambitious: to build a true Lakehouse foundation for DoorDash that let us write data once and read everywhere, with full control over performance, governance, and cost. Fusion is erasing the boundaries between data platforms, eliminating data movement, and delivering instant, unified, and consistent access across different platforms. Unified data asset management is at the core of the Lakehouse paradigm. It breaks fragmented, isolated, reactive silos and transforms them into transparent, cohesive, and consistent ecosystem. So on this slide, I want to highlight two foundational components which we used in Fusion: Snowflake managed Iceberg tables and Databricks Lakehouse federation. Snowflake managed Iceberg tables support read and writes. the table and data and metadata stored in external cloud storage, such as S3 bucket. Snowflake accesses this data using external volume, and that volume allows to set up secure and controlled connection using AWS Identity Access Management. Snowflake Horizon Iceberg catalog delivers end-to-end table lifecycle management, automates compaction, snapshot evolution, and time travel. Open Iceberg REST catalog protocol is vendor-neutral, language-agnostic HTTP API. It powers standard table discovery, governance, seamless cross-engine collaboration. Lakehouse Federation empowers Fusion to discover, query, and govern data across multiple platforms under single Unity Catalog umbrella. It unifies siloed data platforms into one cohesive platform without moving data and enforcing consistent security model. Catalog Federation essentially mounts AWS Glue and Snowflake managed catalog directly into Unity Catalog, enabling unified governance over external data stores. It automatically crawls and asynchronously synchronizes the external foreign catalogs into Unity Catalog. Databricks uniform feature generates both Iceberg and Delta Lake metadata side by side on the same set of Parquet files, delivering seamless cross-engine interoperability without data duplication. So we started with 3 disconnected metadata and 3 separate compute silos and 3 separate compute footprints. Snowflake Island, native Snowflake tables converted to managed Snowflake managed Iceberg tables using Horizon Iceberg catalog, but visible to Snowflake only. Spark, EMR, and Flink Streaming Island. AWS Glue powers Flink and EMR Spark streaming jobs, but all metadata stay locked in Glue. As a result, Iceberg lives only as native open source format, without first-class support in Databricks, and we are stuck with separate catalog silo. Databricks and Trino Island, Unity Catalog's uniform feature support both Delta Lake and Iceberg metadata, but Iceberg metadata not exposed to Snowflake or external Iceberg engines. This design leads to excessive and redundant ETLs, metadata drift, and fractured governance. So in first iteration, we integrate native Iceberg tables produced by Flink or Spark Streaming and the uniform tables managed by Databricks with Snowflake. We wired native Iceberg tables and Databricks uniform tables into Snowflake using its external Iceberg catalog feature. No heavy ETLs, just Iceberg metadata exposed natively in Snowflake. AWS Glue integration. Snowflake assumes IAM role with cross-account trust policy to read Iceberg data table definition directly to external, directly from Glue catalog into external Snowflake Iceberg catalog. Unity catalog integration. Snowflake reads Unity catalog metadata through the Iceberg REST protocol endpoint, authenticating with Databricks service using service principal token. EMR, Flink, and Databricks remain responsible for writing, compacting, and evolving table data. Snowflake simply mounts the external Iceberg catalog and uses auto refresh to stay in sync. Our in-house metadata synchronization application automates the table registration in the Snowflake catalog, so every new table appears in Snowflake without manual intervention in a matter of seconds. So this process proves that Iceberg asset can span Snowflake, Databricks, and streaming engines, but left us juggling fragmented catalogs. In the next slide, I'll demonstrate how we federate everything under one Unity catalog, metadata fabric. In this iteration, we consolidating everything in every catalog under one roof. HMS federation. We federate AWS Glue into Unity catalog, automatically ingesting Glue's Iceberg and Delta Lake metadata using metadata crawls. Native Iceberg tables become read-only uniform tables with both Iceberg and Delta metadata exposed in the Unity catalog. Again, we don't have any data movements here, just instant discovery through the Unity catalog, which now presents the native Iceberg tables as read-only uniform tables, with full support of first-class features of the Unity catalog, including lineage, PII protection, and role-based access control. So just-in-time metadata synchronization, since that whole process, it fires on the first query, or whenever Unity catalog sees stale metadata. Subsequent queries use that copy until the next on-demand refresh is required. The metadata fetch distributed across Databricks compute, which guarantees metadata consistency in a matter of seconds. Why does it matter? So every table now carries both Iceberg and Delta Lake metadata side by side, unlocking Delta Lake tooling, which improves the performance because Databricks engine been working with Delta Lake and optimizing on top of the Delta Lake for a very long time. Analysts and engineers see single consistent namespace in Unity catalog, no more hunting across Glue or Snowflake. Uniform governance in performance. I already mentioned role-based access, lineage, and PII protection. It all works identically whether your source table comes from Glue or Snowflake. This iteration allows us to keep the existing legacy jobs running uninterrupted while consolidating every data set under Unity catalog as our primary metadata store. So let's review the whole picture. Snowflake federation. This is, by the way, great example how we separate compute and storage. The data produced and managed in Snowflake now, without copying to the different platforms, can be consumed, for example, in this case, by any client which connect to the Unity catalog. So just in time, metadata synchronization make it happen. HMS federation. AWS Glue, Iceberg, and Delta Lake Metastore is federated into Unity catalog, exposing legacy Glue tables as read-only uniform Iceberg tables. On the right side, unified access layer now consists of 3 views. Federated Snowflake with read-only Snowflake objects. Uniform tables through the Unity catalog with read and write support from the Databricks clients. And federated Glue, legacy Glue tables, all consumable by Databricks, EMR, Trino, and beyond. So what we have achieved, consolidated metadata foundation spanning batch, streaming, and warehouse engines without moving data or rewriting pipelines, setting us up for the final Lakehouse phase, truly write once, read everywhere. So this slide shows the final catalog consolidation. the new Databricks managed Iceberg format introduced recently by Databricks. It provides true interoperability between various Iceberg clients, including EMR, Flink, and Databricks. We retire AWS Glue as a legacy metastore. No more fragmented catalogs or fragile HMS federation. Managed Iceberg in Unity catalog. All table, metadata, and data now managed in Unity catalog as managed Iceberg tables using the open Iceberg REST API interface. True open source compatibility, native Iceberg clients, EMR, Flink, and as well Databricks can now interchangeably read and write to the same table, which truly creates synergy between different compute engines, allowing the different data engineers to decide which compute to use and use the best tool for the job. Built-in predictive optimization, liquid clustering, and automatic compaction run under the hood, delivering lean storage and faster queries without hand-tuned scripts. Unified role-based access control, masking, lineage, time travel, all enforced by Unity Catalog, eliminates policy gaps and metadata drift. With managed Iceberg tables, front and center, Fusion completes its journey with one open format, one primary metastore, zero data movement, and true write once, read everywhere for every engine. From vision and theory to reality, what have we practically achieved after we unified on Iceberg and single primary catalog? We are on track of transition approximately 30% or more of our Snowflake and data lake assets and correspondent ETL pipelines to Iceberg format. We have cut end-to-end runtime by 5% and slashed data to dashboard latency by 50%. So teams get fresher insights faster. Cost optimization. Average compute and storage costs are down by 30% due to eliminating unnecessary data copy process. Migration automation is facilitated by our IceX utility that let us to onboard a table in just 30 minutes. And we already seen 50% reduction in maintenance effort for our data operations. These results show Fusion turning theory into practice, uniting our data assets under one catalog while delivering unmatched speed savings and scale across DoorDash data platforms. This slide shows how our legacy three-stage ETL pipeline evolves into streamlined Iceberg-powered Lakehouse workflow, eliminating redundant copies, simplifying orchestration, and unifying metadata under one format. So on the left side, the legacy design, ETL design under before title. As you can see, Snowflake ETL step, raw events land in Snowflake native staging table, transformed, then loaded into the native production table. A separate data copy job processes data by pulling on the availability status from the upstream job and loading data into data lake. Basically, it's extracting newly arrived data from the upstream ETL pipeline and loading it to the data lake. But that's not the end of story. And as you can see, it's one of the most resource-intensive and fragile processes. So data lake ETL waits on delta copy to complete before running lake side transformation and populating the final target table in data lake. So pain points, obviously they're pretty apparent. 3 distinct jobs with custom triggers and status checks, brittle and hard to monitor. Same data is written twice, Snowflake and Delta, consuming extra compute and storage. Runtime coordination between pipelines creates failure points and delays. Back and forth transfer increases runtime and cost both Snowflake and Data Lake. On the right, oops, sorry, 1 second, too fast. On the right side, you can see the new design. So prerequisite for the new design is that we load Snowflake managed Iceberg table with the data from the source standard table. We convert existing Snowflake prod table into Snowflake managed table using one-time load. But after that, stage 2 prod ETL job stays the same. Writing directly into this time managed Iceberg table. So just in time, metadata synchronization in kind of highlighted in green box here, exposes Snowflake managed table as first-class uniform data lake in Unity catalog. The data lake process, including signaling and runtime coordination, stays the same. It's just monitoring the availability of the upstream data using standard signaling mechanism. So with this approach, we eliminating data copy, reducing orchestration and maintenance burden. So let's talk about automation and developers' velocity. Why we built IceX? Migrating hundreds of Snowflake tables to Iceberg used to mean handcrafted DDLs, brittle swap scripts, and risky rollbacks. IceX turns that pain into one command workflow, standardizing every step and cutting engineering effort to near zero. IceX consists of two pillars, two-tier workflow. First is IceX local, which used by developers on their local laptops, and developers can run create task command. What that command does, it includes and encapsulates all standard logic which require to develop the transformation scripts. This task pulls source table DDL, table grants, auto-generates deploy script, Iceberg stage table creation, table swap script, grants, row count validation checks, and many other steps which normally require to do it reliably. It also refactors the ETL, which is responsible for normally loading that target table. And we use different approaches, deterministic and Gen AI approaches to reduce the work which is normally required by developer to the minimum. At the end, the project is reviewed in a standard PR process, pushed to production by merging that feature branch from developers' environment to production. The right side pillar, it's IceX development. It's Airflow service. It monitors the submitted tasks, verifies if dependencies are met, executes deploy or rollback, including swap tables and running the various validation methods, including count of the source and target table, writes to audit log, to send Slack notification, and it can do one button click rollback if necessary, if something goes wrong. So IceX transforms migration from heroic effort into routine task, powering our seamless move from legacy ETL to unified Lakehouse, Iceberg Lakehouse. The benefits include Standardization. Every migration follows the same validated playbook, no bespoke SQL or ad hoc shell scripts. Built-in row count checks and command rollback, one command rollback. Keep production risk at minimum. Automation. Audit table and Slack alert fire automatically, no manual status verification is required. Velocity. A new migration task spins in minutes, not days, clearing the path for rapid Iceberg adoption. And as you can see here, it's just example of the Slack message which received by developer after successful deployment and rollback. And as you can see, developer, the same task can be executed in development environment, but also can be executed in production after it's deployed to production. It includes all necessary information, including the name of the table, the data engineer who deployed it, the runtime, validation, but also behind, we also have separate reporting media which describe the entire process in much more details. If process fails by any reason, developer receive detailed information about reason of the failure, and they can retry or refactor the code before retry. So what are the lessons learned and what kind of secret sauce which I want to call out just to make sure I can cover all the kind of secrets that we use to make that process success. First of all, I would call Unity catalog just-in-time synchronization. We spent significant amount of time making sure it works end-to-end seamlessly and reliably. It guarantees sub-second consistency and let Databricks work with external platform and data sets at full speed without manual refresh jobs. Third-party interchangeable writes. True bidirectional write once, read everywhere. Across majority of the platforms, no vendor lock-in, no format gymnastics. Uniform Iceberg integration. ETL pipeline changes are minimal. Role-based access and performance stay intact. The transition step handled behind the scene. These three capabilities turn Fusion, Lakehouse vision into reality. Seamless synchronization, cross-engine writes, and zero-friction orchestration. Yeah, almost done. So in this slide, I listed a few Iceberg format limitations, which, by the way, partially already resolved. Databricks recently announced the release of Iceberg version 3, which addresses quite a few concerns which listed in that slide. With Databricks unification, customers can interoperate across Delta and Iceberg without needing to rewrite data or delete files. This is because Iceberg version 3 feature have compatible implementation across Delta Lake, Apache Parquet, and Apache Spark. The new features include row-level deletes, deletion vectors handling, row ID, which gonna power the incremental load and streaming in future, complex data type handling, such as variant, and a few important other features. So Project Fusion, delivering enterprise-grade performance, governance, and true write once, read everywhere interoperability. And that brings us to the end of the technical walkthrough. I also want to express my sincere gratitude to the Databricks support team, which been following with us and helping us on every step of the implementation of the Project Fusion and contributing to design, troubleshooting, and prioritization the features which we used in this project. So with this, I want to open the floor for the questions.